Good morning or good afternoon, everyone, depending on where you are. I'm Samarakoon, a recent PhD graduate at Monash University, Australia. Today, I'm going to present some of my experimental research work on the topic role of waste glass powder in fly ash slag-based alkali-activated binders. Moving to the background of cement production and consumption, you may know ordinary Portland cement, or OPC, is widely used for most construction applications. It shows extremely high demands, which is only second to water consumption. However, OPC has several drawbacks in its production process because it consumes extensive raw materials, energy, and cost while emitting tons of carbon dioxide to the atmosphere, contributing 8% of the global CO2 emission. Therefore, alternative cements, such as alkali-activated binders, had a great attention over past decade from cement and concrete community. Alkali-activated binders, or AABs, basically composed with two parts: solid precursors and alkali activators. Industrial waste, such as coal ashes, metal slags, generally serves as the solid precursors, and commercial alkali hydroxides and silicates serves as the alkali activators, as shown here. Let's check the applicability of waste glass in alkali activated binders. You know, glass is manufactured by melting a mixture of silicon dioxide, sodium carbonate, dolomite, and limestone at a high temperature up to 1600 Celsius. Every year, millions of tons of glass are generated in the municipal waste glass stream, and less than 10% is recycled due to high contamination of impurities. Some of the different types of glass include soda lime glasses, comes from bottle and containers. Borosilicate glasses comes from chemical apparatus and pharmaceutical wares. Fluorescent lamp glasses, which comes from light bulbs. Lead glasses comes from televisions and electronic parts. Flat glasses generated from motor vehicles and building construction industry. Of these several types of waste glasses, the soda lime type is responsible for highest waste generation, about 80%. Also, soda lime glass generally has high silica and calcium contents than other types of glasses. Therefore, it has the most potential to use as a solid precursor and alkali activator in alkali activated binders. This slide shows the chemical composition and particle size distribution of raw materials, which I used in my research: fly ash, blast furnace slag, and waste glass. In my research, I used waste glass in both ways: as a precursor replacing fly ash and as an activator replacing commercial sodium silicate. I have used fly ash and slag as solid precursors and powdered waste glass mixed with sodium hydroxide as solid alkali activator to cast 1 part alkali activated binder. If you consider waste glass based solid activator powder, our final objective is to prepare sodium silicate, which is a better alkali activator in fly ash slag cement binders. Here, waste glass acts as a silica supplier, and sodium hydroxide acts as the main alkali source to form sodium silicate. In the case of using waste glass as an alkali activator, it was prepared in solid form rather than using liquid and corrosive alkali solutions such as sodium hydroxide or sodium silicates. Therefore, it is called one-part alkali-activated binders, and they have several advantages in handling and mixing at in-situ conditions compared to two-part alkali-activated binders, which use liquid alkali activators. However, soda lime type bottle glass used in this study contains impurities other than silica. Therefore, solid or dry activator produces other silicate and carbonate products with the heat treatment. So the efficiency of producing crystalline sodium silicate in the solid activator need to be assessed. Using X-ray diffraction or XRD, we could identify the mineralogy and then quantify the efficiency of producing crystalline sodium silicate. XRD results show that it produces more than 70% of sodium silicate. These SEM images show the morphology of both raw glass powder and resultant dry activator powder, what we call solid activator, under 1,000 times magnification. Irregular shape and agglomerated nature of dry activator powder is due to newly formed crystalline sodium silicate products with the heat treatment. Dissolution of dry activator was also assessed using ICP or ES tests. These graphs show the dissolution of dry activator in water compared to commercial sodium silicate, abbreviated as NS here, considering 1 hour time period under ambient temperature and pressure conditions. Graph A shows silicon ion release, while graph B shows sodium ion release for both dry activator and sodium silicate powders. Results show a gradual release of silica in dry activator powder compared to commercial sodium silicate. However, sodium ion release is much higher in dry activator than commercial sodium silicate, confirming better dissolution of dry activator in water. Let's check the properties of waste glass incorporated alkali activated binders. This slide shows the strength, microstructure, and mineralogy results of waste glass incorporated fly ash slag alkali activated binders after different curing times. According to the results, alkali activated binder shows sufficient compressive strength, around 30 megapascal after 28 days, and a denser microstructure with increase in replacement of waste glass. It also showed fewer unreacted minerals of fly ash and slag, which we used as raw materials in the hardened phase with the curing time. Therefore, these results confirm that waste glass would be a better alternative as a mineral precursor for one-part alkali activated binders. This slide summarizes the findings of the study, that is, soda lime glass powder can be successfully utilized in both ways, as a mineral precursor and as an alkali activator. Dry activator incorporated one-part alkali activated binder show comparable strengths and a dense microstructure with the curing time. The main hydration product of the hardened binder are calcium silicate hydrate, calcium aluminosilicate hydrate, and calcium sodium aluminosilicate hydrate type gels. Finally, one-part alkali activated binders can utilize up to 17% of waste glass by mass and up to 61% of total cementitious waste by mass in 1 cubic meter alkali activated binder slurry. They are also 23% cheaper and 84% greener, that is emission effective, than commercial activator-based alkali activator binders. If you are interested, you may refer to this publication for detailed results and discussions. This will conclude my presentation, and thank you everyone for your attention.